There is a rule at the heart of quantum mechanics that seems to violate everything we hold dear about logic, causality, and the nature of physical reality. It is a rule that troubled me deeply when I first encountered its implications, and it continues to fascinate and perplex physicists even today. This is the rule of superposition, the principle that a quantum system can exist simultaneously in multiple states that would be mutually exclusive for any classical object. An electron can be in two places at once. A photon can pass through two different slits simultaneously. A particle can spin clockwise and counterclockwise at the same time. These statements sound absurd, contradictory, logically impossible. And yet they are true, verified by countless experiments, and absolutely essential for understanding how nature operates at its most fundamental level. Let me tell you how I came to appreciate the radical nature of superposition, because it was not immediately obvious even to those of us who were building quantum mechanics in the 1920s. When I developed my model of the atom in 1913, I proposed that electrons could only occupy certain discrete energy levels and that they jumped instantaneously from one level to another when absorbing or emitting light. This was already a significant departure from classical physics, where everything changes continuously. But I was still thinking in largely classical terms about what happened between measurements. I imagined that an electron was definitely in one energy level or another, even if we could not predict which level it would jump to next. It was only when Erwin Schrödinger developed his wave equation in 1926 that the full strangeness of quantum mechanics became apparent. Schrödinger's equation describes how the quantum state of a system, represented by a mathematical object called the wave function, evolves over time. The crucial insight is that the wave function can be a combination, a superposition, of multiple different states. If an electron can be in state A with some probability and state B with some other probability, then according to quantum mechanics, before we measure which state it is in, the electron is not secretly in either A or B with us just being ignorant of which. Rather, the electron is genuinely in both states simultaneously, in a superposition of A and B. This sounds like word games or mathematical abstraction, so let me make it concrete with an example that shows why superposition is not just a statement about our ignorance, but a physical reality. Consider the double-slit experiment, which I discussed at length with my colleagues in Copenhagen, and which Richard Feynman later called the central mystery of quantum mechanics. We send electrons one at a time toward a barrier with two narrow slits cut into it. Behind the barrier is a screen that records where each electron arrives. If we close one slit and leave the other open, we get a simple pattern on the screen, roughly aligned with the open slit. If we close the other slit instead, we get a similar pattern aligned with that slit. Now, here is where it gets strange. If we open both slits and send electrons through, we do not get the sum of the two individual patterns. Instead, we get an interference pattern, alternating bands of high and low probability, exactly like what happens when water waves pass through two openings and interfere with each other. The only way to explain this mathematically is to say that the wave function of each electron passes through both slits simultaneously, and these two components of the wave function interfere with each other when they reach the screen, creating regions where they reinforce each other and regions where they cancel out. You might object that perhaps the electrons are somehow interacting with each other, creating this pattern collectively even though each one only goes through one slit. So we modify the experiment. We turn down the intensity so that electrons go through one at a time, with long intervals between them, ensuring that each electron completes its journey before the next one begins. What happens? Each electron still arrives at the screen at a single point, making a tiny dot. But as we accumulate thousands of these dots, they build up the same interference pattern. Each individual electron, traveling alone through the apparatus, is creating an interference pattern that can only be explained if that electron somehow went through both slits simultaneously. This is superposition in action. Before the electron hits the screen, it is in a superposition of having gone through the left slit and having gone through the right slit. Both possibilities are real components of its quantum state. The electron has not secretly chosen one path with us being ignorant of which. It genuinely exists in both possibilities at once, and this superposition is what allows the wave function components from both slits to interfere and create the observed pattern. Now comes the part that truly defies logic. If we place detectors at the slits to determine which one each electron passes through, the interference pattern disappears completely. We get two simple bands on the screen, exactly what we would expect if each electron went through one slit or the other like a classical particle. The very act of measuring which slit the electron goes through destroys the superposition. The wave function, which previously encompassed both possibilities, collapses to a single definite state corresponding to one slit or the other. And once this happens, there is no interference because interference requires the superposition of both paths. This is what makes superposition so difficult to accept logically. It seems to violate the law of non-contradiction, one of the most basic principles of logic since Aristotle. A thing cannot be both A and not A at the same time. An electron cannot be in two places at once. And yet quantum mechanics insists that it can, at least before we measure its position. The resolution to this apparent paradox is that quantum states are not classical states. When we say an electron is in a superposition of two locations, we are not saying it is fully present at both locations in the way a classical object might be in one definite location. We are saying that its quantum state is a mathematical combination of states associated with both locations, and this combination has physical consequences, like interference, that prove the superposition is real and not merely a statement about our lack of knowledge. Let me give you another example that illustrates both the reality of superposition and its deeply counterintuitive nature. This is Schrödinger's famous cat paradox, which Owen proposed in 1935 not as a serious scenario but as a way to highlight what he saw as the absurdity of the Copenhagen interpretation that I and my colleagues were advocating. Imagine a cat in a sealed box with a vial of poison, a radioactive atom, and a detector. If the atom decays, the detector triggers a mechanism that releases the poison and kills the cat. According to quantum mechanics, the radioactive atom is in a superposition of having decayed and not having decayed until we measure it. Therefore, by the logic of quantum mechanics, the cat should be in a superposition of being alive and being dead until we open the box and observe it. Schrödinger thought this was ridiculous, and in a sense, he was right to be troubled. We never observe cats in superpositions of alive and dead. We never observe macroscopic objects in such superpositions at all. So either quantum mechanics does not apply to large objects, which seems arbitrary, or something happens as we scale up from atoms to cats that destroys superpositions, turning them into classical either-or situations. I argued at the time, and I still believe, that the resolution lies in recognizing the crucial role of measurement and the boundary between quantum and classical descriptions. A cat is not an isolated quantum system. It is constantly interacting with its environment, with air molecules bouncing off it, with thermal radiation, with countless other particles. These interactions entangle the cat's quantum state with the quantum states of environmental particles in an incredibly complex way. This process, which we now call decoherence, effectively destroys the quantum coherence that would be necessary for superposition effects to be observable. The superposition is still there in some technical sense, but it is spread out over such an enormous number of environmental particles that it can never reassemble to show interference effects. Moreover, and this was central to my thinking, we must maintain a distinction between the quantum system being measured and the measuring apparatus. The apparatus, which in this case includes the detector, the poison mechanism, and arguably the cat itself, must be described classically. We must be able to say definitively that the detector either did or did not register a decay, that the cat is either alive or dead, because we need to communicate our results using ordinary language and classical concepts. If everything were described quantum mechanically with no classical level at all, we could never actually report definite outcomes, and physics would lose its empirical content. This interplay between quantum and classical descriptions troubled many people, and it still does. Where exactly is the boundary? What counts as a measurement? Why does the wave function collapse when we measure but evolve deterministically according to Schrödinger's equation when we do not measure? These are profound questions, and I confess I do not have answers that will satisfy everyone. But what I can say with confidence is that superposition is real, that it has been verified in countless experiments, and that any complete understanding of quantum mechanics must grapple with this apparently illogical feature. The violation of classical logic becomes even more stark when we consider quantum entanglement, which is really a form of superposition involving multiple particles. When two quantum systems interact and then separate, they can remain in an entangled state where their properties are correlated in ways that cannot be explained classically. The canonical example involves two particles with spin. Spin is a quantum property with no real classical analog, though we use the word spin because it behaves mathematically like angular momentum. Imagine we have two electrons in a special quantum state where the total spin is zero. This means that if we measure the spin of one electron along any axis and find spin up, the other electron must have spin down along that same axis to maintain zero total spin. Now, here is where it gets strange. Before we measure, either electron has a definite spin along any particular axis. Each electron is in a superposition of spin up and spin down. But the two electrons are entangled, meaning their spins are correlated. The combined system is in a superposition of multiple possibilities: electron 1 spin up and electron 2 spin down, electron 1 spin down and electron 2 spin up, and similar correlations along all possible axes. When we measure the spin of one electron along a particular axis, we instantly know the spin of the other electron along that same axis, even if the two electrons are now separated by enormous distances. Einstein called this spooky action at a distance, and he thought it proved that quantum mechanics must be incomplete. How could measuring one electron instantaneously determine the state of a distant electron? Einstein argued that the electrons must have had definite spin values all along, predetermined when they interacted, with quantum mechanics merely reflecting our ignorance of these hidden properties. But here is the crucial point that shows superposition is genuinely non-classical. If the electrons had definite spin values from the start, just hidden from us, then certain mathematical relationships called Bell's inequalities would have to be satisfied in the correlations between measurements along different axes. But quantum mechanics predicts violations of these inequalities for entangled states, and experiments have consistently confirmed the quantum predictions. The electrons genuinely do not have definite spin values until we measure them. They are in superpositions that only collapse when measurement occurs, and the entanglement means that measuring one electron instantly affects the state of the other, not by sending a signal faster than light, but by collapsing the shared entangled state. This is superposition at its most powerful and most paradoxical. Two electrons can be in a state where neither has definite properties individually, yet their properties are perfectly correlated when measured. The combined system is in a superposition of multiple joint possibilities, and this superposition is a real, physical thing that can be verified experimentally through the violation of Bell's inequalities. There is no classical way to explain these correlations. We must accept that quantum superposition is genuinely how nature works. Why does superposition defy logic? Because logic as we know it, Aristotelian logic with its law of non-contradiction and its assumption that propositions are either true or false, was developed based on our experience with macroscopic objects that never exhibit superposition effects. In our everyday world, things are either here or there, either moving or stationary, either one color or another. We never see objects in superpositions of mutually exclusive states because decoherence from environmental interactions instantly destroys such superpositions at the macroscopic scale. But at the quantum level, where systems can be sufficiently isolated to maintain coherence, superposition is ubiquitous and essential. An electron in an atom is in a superposition of multiple energy levels until we measure its energy. A photon is in a superposition of multiple polarizations until we measure its polarization. A quantum computer, to the extent we can build one, stores information in quantum bits that exist in superpositions of 0 and 1 simultaneously, allowing certain computations to be performed with exponentially greater efficiency than classical computers. Some physicists and philosophers have tried to develop new logical systems, quantum logics, that would be appropriate for describing quantum phenomena without the paradoxes that arise when we apply classical logic. In these systems, the law of non-contradiction might be relaxed or modified to allow for superpositions. I have some sympathy for these efforts, but I have always felt that the problem is not with logic per se but with the attempt to force quantum phenomena into classical conceptual frameworks. Quantum mechanics is perfectly consistent mathematically. The Schrödinger equation governs how wave functions evolve. The Born rule tells us how to calculate probabilities from wave functions. The formalism is rigorous and unambiguous. The difficulty arises when we try to visualize or describe in ordinary language what the mathematics is representing. This is where my concept of complementarity becomes relevant. I argued that we should not expect to be able to describe quantum systems using a single, unified picture that captures all their properties simultaneously. Instead, we need multiple complementary descriptions that are mutually exclusive but all necessary for completeness. Wave and particle are complementary. Position and momentum are complementary. Different experimental arrangements reveal different aspects of quantum reality, and these aspects cannot be combined into a single classical picture because they involve superpositions that collapse differently depending on what we measure. Superposition defies logic because logic presumes that things have definite properties that we describe, whereas quantum mechanics shows that properties often do not exist in definite form until brought into existence by measurement. The electron going through a double slit is not secretly going through the left slit with us being ignorant of this fact, and it is not going through the right slit with us being ignorant of this fact. These are not the only alternatives. There is a third possibility that has no classical counterpart. The electron is in a superposition of both, and this superposition is what allows interference. I spent many years defending this view against critics who found it too radical, too strange, too contrary to common sense. Einstein, in particular, never accepted that quantum mechanics was complete. He felt that nature must have an underlying definite reality, and that quantum mechanics merely described our limited knowledge of this reality. We had many discussions, some quite heated, though always respectful. I tried to explain that the demand for an underlying classical reality was itself a prejudice, a holdover from centuries of classical physics that we needed to abandon in light of experimental evidence. The experiments have vindicated the quantum view. Superposition is real. It has been demonstrated not just with electrons and photons but with larger and larger systems. Researchers have created superpositions of molecules containing dozens of atoms. They have created superpositions of mechanical oscillators, tiny mirrors that exist in superpositions of being here and there simultaneously. The quantum world is not limited to the ultramicroscopic. It extends as far as we can maintain coherence and isolate systems from decoherence. And yet, for all its strangeness, superposition is the key to understanding chemistry, materials science, and increasingly, technology. Chemical bonds form because electrons and atoms exist in superpositions of multiple orbitals, creating the intricate patterns of electron density that determine how atoms interact. Superconductors work because electrons pair up and enter collective quantum states that are superpositions of many possible configurations. Quantum computers, if we can build them at scale, will harness superposition to perform calculations that would be impossible classically. The quantum rule that defies logic, the rule of superposition, is not a curiosity or an anomaly. It is fundamental to how nature works. And the defiance of logic is not a flaw in nature but a revelation that our logic, developed for classical objects, is too narrow to capture the full richness of physical reality. We must expand our conceptual frameworks, accept that nature at its most basic level operates according to principles that seem impossible from a classical perspective, and recognize that this strangeness is not something to be explained away but something to be embraced as a profound truth about the universe. When I say that superposition defies logic, I do not mean that quantum mechanics is illogical or inconsistent. The mathematical structure of quantum mechanics is perfectly rigorous. What I mean is that it defies the intuitive logic we have developed from everyday experience, the logic that says things must be definitely one way or another, that contradictions are impossible, that properties exist independent of measurement. Quantum mechanics teaches us that this intuitive logic is an approximation, useful for macroscopic objects but inadequate for the quantum domain. I have lived with these ideas for so long that they have become second nature to me, but I remember how difficult they were to accept initially. The idea that an electron could be in two places at once, that measurement creates reality rather than revealing it, that particles separated by vast distances could have instantaneously correlated properties, all of this seemed impossible, absurd, logically incoherent. But the mathematics worked. The predictions matched experiments. And gradually, I came to see that the problem was not with quantum mechanics but with my own expectations about what physics should look like. The quantum rule that defies logic, superposition, is perhaps the most important discovery in 20th century physics. It forced us to reconsider the nature of reality, causality, measurement, and knowledge itself. It showed us that the universe is far stranger than we imagined, that nature operates according to principles that transcend our everyday intuitions, and that accepting this strangeness is the price of understanding the physical world at its deepest level. Superposition is real, it is everywhere in the quantum realm, and it is the foundation on which all of modern physics and chemistry is built. The logic it defies is merely human logic, shaped by macroscopic experience. The logic it embodies is nature's logic, quantum logic, the true logic of the fundamental constituents of reality.